Cramer. Okay, next up, John Cramer, who's going to talk about the stuff that's further out. Really further out. And as I said before, I recommend that you read his chapter in the book because it's really a terrific account of all of those subjects at great depth and great perception. John Cramer is best known to this community for his columns in Analog. But he also has a day job at the University of Washington in Seattle, in which he has done experiments in theory on various aspects of quantum theory and in experiments as well. So he's a very well-rounded person and a long experience in this field and writes a terrific column in Analog, which you can read online. John?
I was hoping for a potty break first, but I guess I can manage. Okay, so at the Orlando Starship Symposium, I was given the responsibility of doing the exotic paths to the stars, basically exotic physics. Exotic here means that you need at least one visit from the tooth fairy in order for the thing to work. Let me start by, let's see, how do you make this thing go? Where do you click? There. Oh, there's the keyboard. Okay.
There's the up down. That's
right.
Really all you need.
Okay.
Here's the mouse.
Well, all I get is a.
There. Down.
There. Okay.
Down. Hit the down here.
Down. Okay. All right. So basically the two areas that were covered in Orlando were space drives. And then warp drives and wormholes. And I'm going to devote one slide to giving you sort of an overview of this, and then I'm going to go on to one specific thing that I wanted to talk about. Space drives here basically means things that seem to get around Newton's third law so that you don't have to send reaction mass out the back to make the thing go forward. I have a particular interest in this. Jeff Landis said yesterday how he had used his first programmable calculator to investigate a nuclear propulsion or something. When I was in high school, I invented a space drive. It involved sending little weights around in various ways in peculiar orbits, and I even spent some time in my uncle's machine shop trying to build a working model of it. But I spent considerable effort when I was an undergraduate physics major to understand enough physics so I could understand why it didn't work. And I was able to prove a general theorem showing that devices like that can't work, which is probably better than building a working model. Anyhow, these things are, Mark Millis gave a very nice talk at the Orlando Symposium in which he listed 27 bad ideas for building a space drive. None of them, I would say, are ready for prime time. Perhaps the most promising is James Woodward's approach using Mach's principle, but there are still some details in that need to be worked out, and I'm not going to talk about it today. But I say a little bit about this in the symposium book that's just come out. The second topic is warp drives and wormholes. Basically, when I was an undergraduate and graduate student learning about general relativity, what you did was to take a mass distribution, or a distribution of massive objects, and calculate how it's distorted space, and produced a metric that described the structure of the space warp that's generated by gravity. People have more recently turned this around and said, hey, let's produce some interesting warped space things and that do interesting things, and then figure out what kind of mass distribution we need to do this. This has been labeled as metric engineering. And some of the things that have come out of this, basically starting with Einstein, are the idea of warp drives and wormholes. The problem is that when you actually calculate what kind of matter distribution you need, it turns out that in almost all of the cases that have been looked at, you need negative mass, and we've never found any negative mass in the universe, which creates a certain problem. There are some approaches which seem to get around this by using other exotica that come out of general relativity. For instance, cosmic strings. Matt Visser has a species of wormhole that is held open by having a cosmic string of negative string tension in the middle of the wormhole mouth, pushing it out while the wormhole tries to collapse in some sort of delicate balance. So I guess I'm not sure whether that counts as one or two visits from the tooth fairy, but at least it seems to be a possible solution. Okay, and the other thing I wanted to say is that at my request, we got one of the theorists who have been working in this area sort of as critics. The basic idea here is that general relativity seems to allow you to do all kinds of weird things involving wormholes and warp drives and faster than light and creating space and annihilating space and so forth. And the question is, can you really get away with this? Is nature really going to allow you to do that? And some people have thought that probably the thing that would stop you from using general relativity in those ways is that a theory that we really only know the name of at the moment, quantum gravity, might come in and prevent this kind of abuse of general relativity by stopping you from doing these things. And so they have used this as a way of trying to get some purchase on quantum gravity itself, and they've made some progress. Basically, the approach they've been using so far is to use quantum field theory to to provide sort of limiting conditions for certain things that you might want to do with general relativity. I'm a little suspicious of this because when you apply quantum field theory to calculating the cosmological constant, you get a number that's only off by 10 to the 50th orders of magnitude. And this is the kind of approach of quantum field theory that they're applying to general relativity. So I'm a little bit suspicious of these things that are coming out. Okay, that's about all I wanted to say about the symposium. We had a lot of interesting talks there, and I've summarized them in the new book that's come out, and I advise you to look at it. Now I want to change the subject a little bit and talk about one particular thing. Here I'm assuming that along with other people who have done calculations about wormholes, that there is some way of producing stable wormholes. And I wanted to talk, and then I want to look at a little bit at the implications of this for interstellar travel. Basically, this is an end run in which I'm trying to get around the massive problems that we've been hearing about all morning of building massive spaceships that cost trillions of dollars. And it solves another interesting problem as well. Almost all of these approaches, at least all of them that I know about, even if you went to the stars, you couldn't come back because it would take so long that you wouldn't be able to return home in a reasonable time. The human lifetimes are involved, and even if you use relativistic time dilation, you can't go back. The technique I'm going to talk about, you can go home anytime you want. So let's continue on with this. Oops, I guess I went the wrong way. This is an early attempt at wormhole physics by Hieronymus Bosch. We see that various people are being transported through the wormhole to the other side and arriving in heaven. Presumably there's another wormhole that goes in the other direction around someplace, but Bosch didn't show us that in this particular painting, which is called the Ascent of the Blessed, and it's in the Palace of the Doge in Venice, Italy. More recently, Albert Einstein and his colleague Nathan Rosen published a paper in 1935, and this was the original, this was the initiation of the idea of wormholes. Basically, what Einstein and Rosen were trying to do was to understand what fundamental particles are. And they proposed that a fundamental particle might look something like this, that you have a wormhole in space that has electric lines of flux going through it, and the end of the wormhole where the lines of flux go in looks like a negative electric charge, and the end of the wormhole where the electric flux lines come out looks like a positive charge. And so they hypothesized that, for example, electrons and positrons might be just ends of wormholes with electric flux lines threading through them. Later, John Wheeler and one of his colleagues calculated, first of all, the mass that this would have to have. It turns out that this is not going to be a mass of an electron. It's going to be something in excess of a Planck mass. And secondly, that it would be, this is basically unstable, and it would close up so rapidly that you wouldn't be able to even shoot one photon through it if it spontaneously opened up before it closed again. That was somewhat the end of the story. But people continued to think about this, and it became known as an Einstein-Rosen bridge. Later on, John Wheeler rechristened Einstein-Rosen bridges and called them wormholes, and this terminology has become standard. However, my science fiction novel, Einstein's Bridge, goes back to the older terminology and refers to these things. Okay, this brings us to 1988, when the whole idea of wormholes was reinvestigated by Kip Thorne and his group. Basically, I guess what happened here was that Carl Sagan had a big book contract for writing a science fiction novel, and he was fishing for a plot, and he wanted to use wormholes in order to do it. So he went to Kip Thorne and said, well, what about this thing of wormholes? What about these Einstein-Rosen bridges? Is there any way of using those for interstellar travel? And Thorne told him that they were unstable, it had been demonstrated, and so forth. And then he got to thinking about it, and he decided that this hadn't been investigated enough. And so he sent one of his brighter students, Mike Morris, to look into it. And they concluded that, yes, you could stabilize wormholes under certain conditions. And they came up with a scheme involving using the Casimir effect in order to do it. And this is a quote from the paper. One can imagine an advanced civilization pulling a wormhole out of the quantum foam and enlarging it to classical size. This might be analyzable by techniques now being developed for the computation of spontaneous wormhole production by quantum tunneling. And they go, okay, so I'm going to assume that such advanced technology could, by choice, keep a stabilized wormhole very small, so that in the spirit of Einstein and Rosen, one mouth of the wormhole can be considered to behave like a charged particle that has mass m and charge q, whatever those happen to be. Okay, now the other thing that Kip Thorne and company demonstrated was that you can use such a wormhole to produce a time machine. And basically the way you do it is by taking one mouth of the wormhole and putting it on board a relativistic spaceship. Well, you'd have to build one of these things we were just hearing about from Adam, and that would approach some fraction of the speed of light. But you send it off into the cosmos on a little trip, and then you bring it back again, and it's going at some fraction of the speed of light during this leg of the trip and that leg of the trip. And this produces the effect that's well known in special relativity called relativistic time dilation. Basically, the clock slows down. And so this end of the wormhole, the clock is ticking at the normal rate, whereas this end of the wormhole, the clock is ticking qualitatively slower. And so it ends up being younger on this side than it is on that side. Though the wormhole, instead of connecting two regions of space at the same time, become a time-like wormhole in which the connection is across between, say, it goes 15 years here versus 10 years there, or something like that. So it basically becomes a link that you could use to go backwards and forwards in time. Now, nature probably doesn't like you to do that because it causes all kinds of problems with causality and so forth. But nevertheless, it seems this is one of the things that general relativity seems to implement. Morris, the trick is, as I said, is to put one mouth of the wormhole in a relativistic spaceship so that it stays young. Okay, now Stephen Hawking had something to say about this. I found this on the internet and I couldn't resist using it. I apologize if anybody's offended. Stephen Hawking had something to say about this. He said that he thought that there were things in general relativity and quantum gravity that would forbid the advent of time-like loops, such that you might get it with a wormhole. Basically, he pointed out that there were certain formulas for quantum vacuum fluctuations, which have in the denominator the interval, the space-time separation between two objects, such that when this interval goes to zero, you're dividing by zero and things blow up. And so he suggested that there was something called chronology protection, in which the quantum vacuum fluctuations, if you tried to make a wormhole become a time machine, would explode. The quantum vacuum fluctuations would explode exponentially and destroy the time machine and probably the physicist who was trying to make it. So chronology protection is protected. Historians can keep their jobs, and time machines become time bombs. Hawking thinks that nature abhors a time machine, basically, and he may be right. However, as we will see, it may be possible to use the time-like aspects of the wormhole in a way that doesn't violate chronology protection and by creating time-like loops. Okay, so one of the things I want to point out before going any further is a little appreciated property of wormholes called back reaction. What's involved here is that there are certain rules involving conservation laws that apply even to wormholes, and some of the uses of wormholes in science fiction, for example, having a wormhole aboard a spaceship that provides fuel through the wormhole so that you don't have to carry reaction mass with you, would not work because of back reaction. Back reaction is, in a sense, the changes required in the wormhole portal such that various conserved quantities like mass, energy, momentum, charge, and angular momentum are locally conserved at both ends of the wormhole. You can't, if you pass an electric charge through a wormhole mouth, the entry mouth acquires the exact charge that went through, and the exit mouth acquires the opposite charge. The same is true for mass and momentum. This is a problem, but it also is maybe an advantage. For example, it allows you to take a wormhole mouth and charge it to some arbitrary value. Here we have a little circuit where we run an electric current through a wormhole mouth, and this mouth acquires a positive charge, and this mouth requires a negative charge. And you can, as I said, you can do the same thing with mass and with momentum. Okay, now let us suppose that we want to accelerate a wormhole mouth. We have a machine that in principle can do this. The Large Hadronic Collider at CERN is designed to accelerate protons, and as a matter of fact can accelerate any other particle provided it has the same charge to mass ratio as a proton to near light speed velocities. In physics, we characterize the acceleration not by how close it gets to the speed of light, which is always an uncomfortably small little fraction to worry about, but in terms of the Lorentz factor, the amount by which the mass increases of the particle that's being accelerated increases because it's going so fast, or the factor by which time slows down in some clock that's moving with that velocity. This is called gamma, and in the case of the Large Hadronic Collider, the design value of gamma when the protons are running at full energy, which they're not quite yet, is 7,455. What that means is that a proton that's been accelerated by the LHC weighs 7,455 times more than it would at rest, and its little internal clock slows down by a factor of 7,455. Therefore, if we take one of our wormhole mouths and give it the same charge to mass ratio as a proton, we can borrow the LHC for a little while and accelerate it up to the same Lorentz factor. This would require that we give the wormhole a charge to mass ratio of 9.579 times 10 to the 7th coulombs per kilogram, which is the charge to mass ratio of a proton. Now, there may be some problem with doing this. That's a lot of charge if the thing is fairly massive. But there were other ways of accelerating wormholes. The whole structure of the LHC, all of these superconducting magnets and things, are not really there to accelerate the protons. They're there to bend them in a circle so that some local electric fields can accelerate them over and over and over again until they get to the velocity you like in RF cavities. If you had the mastery of wormholes, you could build a very simple accelerator which could reach the same energies as the LHC by just having one wormhole mouth on one side of the RF cavity and the other on the other side, and just sending it through again and again and again. This would, for the purposes of accelerating wormholes, this is perhaps questionable, because the question is whether one wormhole can pass through another. And I don't propose to, as Jim Benford said, that's a gnarly question, and I don't think I want to get into it right now. But anyway, this is a thought experiment in which we're accelerating a wormhole up to that. Okay, what can we do with it after we do that? Well, I want to introduce you to an idea you may have seen before called proper time. This is a term in special relativity. Proper time is the elapsed time between two events as measured by a clock that passes through both events. The proper time depends not only on the space-time separation of the events, but also on the motion and in particular the velocity of the clock. A rapidly moving clock measures a small elapsed time between two events. So d tau, the proper time between two events, is the dt, the event that some external observer would see, divided by the gamma factor, which is how fast the clock is moving. And this is this 7,555 number that we were looking at before. So as viewed through a wormhole, time, if you can look through the wormhole and see what's going on the other side, your view takes place in proper time, so that events separated by a very long time, for example, launching an object from the Earth and arriving at a distant star, appear very much shorter by the time duration of 1 over gamma as viewed through the wormhole. Okay, so NASA recently announced the discovery using the Kepler mission of one of these Goldilocks planets. It's called Kepler. It has the compelling name of Kepler 32e, and it's 1,200 light years from the Earth. So let us imagine that we had one of these accelerated wormholes and we wanted to use it to see what was going on in Kepler 32e. Okay, so we launch a wormhole from the super collider, pointing it in the right direction, and it travels at very nearly the speed of light. It travels 1 part in 7,455, roughly 1 part in 7,455 less than the speed of light. And so it would arrive, as far as our view through the wormhole is concerned, in just 59 subjective days. In other words, looking through the wormhole, we see it leave here and arrive there 59 days later, even though it's traveling at nearly the speed of light for about 1,200 years. Okay, how can that be? Well, it's because the wormhole has become a time machine, and we're seeing we have now a time machine that connects the departure and the arrival in a very small time interval. Okay, now the question is, how could you point at that accurately? And the answer is you don't really have to, because due to back reaction, you can send momentum through the wormhole that can steer it in whatever direction you want. So you can shoot electron beams through it, for example, or light beams that give it steering corrections on the way so that you can manipulate it so that it goes where you want. Furthermore, there's the problem, as Jim was alluding to with the star wisp, of stopping when you get there. And so how could you do that? Well, what you can do is to steer the wormhole so that it goes through the star itself, slowing down. It's a very highly charged particle, very highly ionizing, And so when it goes through a medium like gas, it will, it will lose energy like crazy going through. And so you can imagine that you can put it into some kind of a orbit that repeatedly goes through the stellar atmosphere or maybe even the body of the star itself until it slows down enough so that you can direct it in some direction that you want. In the progress, there will be considerable mass passing through the mass, and this will cause the wormhole mouth to gain energy by back reaction. But this can be compensated by sending low velocity mass through in the other direction. The large charge can be reduced at the same time by sending charged particles through, or it can be maintained by sending particles of the same charge through. If you find a habitable planet there, the wormhole mouth can be brought to the surface, samples extracted, and ultimately you can expand it, sending robot precursors and planetary explorers and colonists and freight right on through. And if the colonists don't like what they see in the other end, they can just step right back through the wormhole and they'll be back where they started without having to worry about having their colleagues having aged by thousands of years while they were gone. What about chronology protection? Well, let's assume Stephen Hawking was correct and that wormholes are prevented from becoming time machines by the equations of general relativity and quantum gravity. What about this for our starships? Well, the wormhole link has a space-like time separation, and what we mean by this is that it spans a distance in time that is slightly less than its distance in space by 1 part in 7,455, and therefore it does not represent a time-like loop, and it does not offer the possibility of producing a time bomb explosion of vacuum fluctuations. The problem might arise, however, if you established a colony at another star, and then you tried to do this again, providing another wormhole link. In that case, you might very well produce a time-like loop. So the moral is you can proceed to explore the stars by sending wormholes in well-separated directions, but do not interconnect them. Don't try to make a network of wormholes, because you would don't cross the beam. Right. So in summary, assuming that stable wormholes exist and that we can master the physics and engineering of microscopic wormholes, we may be able to use them to explore the stars and to colonize extrasolar planets. The time-spanning properties of relativistic wormholes can be used to reach distant star systems in very short times, on the order of days or weeks or months. And wormhole time link connections to the present when the wormhole is launched to the future means that you can go there without having to wait. Basically, you're creating an Einstein-Rosen bridge to the stars. Now, I should also point out that this idea I presented in a 1990 column, so it's been around a while. And as far as I know, no science fiction writer has taken it up as a basis for a story, so I'm still looking for that. One final note, if this is possible, we have the Fermi paradox. Why isn't some advanced civilization already shooting wormholes in our direction, wormhole mouths in our direction this way? Well, if you look at the cosmic ray literature, there is things called Centauro events. And the Centauro event is peculiar because it seems to be a very highly charged, a very high velocity particle that doesn't seem to have any strong interactions. And as a matter of fact, if you ask yourself, what would a wormhole look like that was plowing through our atmosphere, it would look like that. And so perhaps somebody is out there knocking at our door with fast wormholes and we haven't realized it yet. Okay, thank you.
I'll take the first question. I want to ask the first question. What Centauro events, they don't participate in strong interactions. What do they participate in?
They make lots of electromagnetic interactions with the electromagnetic process, but they don't make pions and kaons and things in the process. There is usually a balance that you expect from a cosmic ray in terms of producing things electromagnetically and producing things with a strong interaction, and they're deficient in the strong sector.
Hi, John. Interesting, but your method for accelerating wormholes is unnecessarily complicated, given conservation of momentum. All you have to do, you don't actually have to put the wormhole into the accelerator. All you have to do is push momentum into one mouth of the wormhole, and it shows up at the other mouth.
Yeah, that's very
So
true.
you can just
that's
shine,
the back reaction thing, yeah.
So just shine the beam into one mouth, and it accelerates the other mouth.
Okay, that's a good
really
point.
very
You might
easy.
have to do that for a while.
You have to do it anyway because you have to have a certain amount of momentum accumulated. So either way, but it's just a lot simpler if you don't try to charge the wormhole and accelerate.
Right.
Another comment, by the way, the wormhole that you were talking about spans a distance of about, 1,500 light years. And you said,
yeah.
well, you can't have a network of wormholes. But to make sure you have chronology protection, nobody can have another wormhole traveling in the opposite direction through time in a distance of 1,500 light years. So once you've set up this wormhole network, you are preventing other people from setting up wormholes over a distance of 1,500 light years. And you can only do it if nobody has the opposite polarity time machine within that distance.
Right.
So essentially what you're proposing is an experiment to test how far away is the nearest extraterrestrial civilization that has wormholes. So if you set up a wormhole 1,000
and you blow them up in the process.
At the point where your wormhole blows up, you say, okay, that's how far
there they
it
are.
is
Yes, this is
to the next nearest wormhole network.
Right. This is a completely new approach to SATI. Yes.
It's not quite true what you said, that there is no negative energy. You can certainly, using quantum field theory, create regions of negative energy density, but the equipment that you need to do that itself has a vastly greater amount of positive energy. So overall, if you take the whole system, we haven't yet got anything with negative energy. But if you do have such a thing, as Hermann Bondi pointed out in the 1950s, if you have a negative energy mass, all you need to do is put it next to a positive energy mass. They repel gravitationally.
Right.
They self-accelerate, and that's your starship.
Yeah, this is a lovely idea, as you say, of Bondi's. If you have a negative mass and a positive mass with a sort of a rod between them or something like that, the negative mass repels the positive mass, and the positive mass attracts the negative mass, and so they go zipping through space with a little space drive. How you connect that to a ship in order to make the ship do the same thing, I've never been quite sure, but whether you can actually use this as a space drive if you had a negative mass. But I think the connection problems give you some difficulty, because if you push on a negative mass, it doesn't move in the direction you think, because it has negative inertia and moves in the other direction.
That's the point. They move the same way.
Yeah, but that's just this dipole, and it's not so interesting to have a mass dipole moving through space. You'd like to hook it to your spaceship so that it can push the whole thing through.
You have your spaceship as your positive mass, and you have a negative
Well,
equivalent mass next to it, and it'll just self-accelerate.
I think it's hard to keep the negative mass there.
Well, there's maybe stability.
So I have two questions.
Yeah.
The first one is on when I studied this, the geometry of the Einstein-Rosen bridge. Basically, usually you study as two asymptotic Schwarzschild geometries, and you solve the boundary conditions on that satisfy the Einstein equations. But
no, I've done no mathematics on this at all.
No,
I mean, this
okay,
is a hand-waving idea. Yeah.
Okay, but my understanding is that there is no real framework on, at least on classical gravity, to understand topology change in space-time. So I was wondering if you were aware of a formal framework where we can talk about topology change of space-time. And
I guess I don't understand what you're saying. The general relativity in general does changes the topology of
Yeah.
space-time by warping space according to some metric produced by the local mass distribution.
Usually that's just differential. It's just saying what's the local curvature in space-time, but it's not explaining how the trivial Minkowski topology, which is the flat space-time, asymptotically flat, changes to something which is equivalent to a space-time with handles, which is what one intuitively thinks about.
I guess I would have to refer you to a book published by the American Institute of Physics called Lorentzian Wormholes by Matt Visser, and that's the key, the general reference to the general relativistic description of wormholes in this kind of geometry.
The second question is really quick. When Kerr black holes are usually postulated that they connect two asymptotic flat spacetimes, and they are usually proposed as a way to connect two universes. So, but this flies in the face of the common knowledge that string theorists are talking these days about unitarity. So, and the idea is that if a black hole needs to satisfy unitarity, everything that enters in the event horizon needs to get out eventually. So how do we match conceptually those two apparently contradictory notions? Thank you.
Okay, I was not talking about black holes, but let me tell you my opinion about the question you just asked. Black holes are not forever because they have a finite temperature and they undergo Hawking evaporation. So if you wait long enough, any black hole that forms in a universe that lasts a very long time will eventually evaporate and be gone. And so what you put in will go out. And so, but beyond that, I don't have any comment. Yeah.
Just a little postscript to your story about Kip Thorne and wormholes. When we started working on the film version of Contact, Carl asked me to talk with Kip about what wormholes would actually look like.
Yeah.
And his first comment was, well, the main thing is don't make them look like black holes. They're not swirling disks, going down a drain.
Right.
And he assigned me to work with his student, Scott Hughes, on how a wormhole would actually look, which is not like a hole at all. It's actually convex. It would look like a blister in space, and you'd see an inverted image. Scott calculated the paths of the photons. You'd see an inverted image of where you were going in the wormhole. So I did some storyboards showing that, which are actually on display outside. And when I showed them to the director and said, now this is something that nobody's ever shown before. This is something new. And they said, yeah, that's nice, but what we really want it to look like is water going down the drain. And that's how it looks in the movie.
I see.
No more questions? I'm surprised that anybody has questions about such a pedestrian topic.
I once read somewhere that someone said that exploding galaxies were industrial accidents, and I wondered just how big the bang is if you get these wormholes doing these bad things.
Well, I guess all that happens, if the quantum vacuum fluctuations build up high enough to prevent the time-like loop from forming, I think that's really all that's needed, and so that probably doesn't represent a very big explosion. But I haven't. There are papers about chronology protection and these kinds of things that I've read, but they never exactly address that issue of how big the disruption of space-time is if chronology is being actively protected like that. So I don't really know the answer to that, but I doubt that it would explode a galaxy.
So I was curious, what has been proposed or done experimentally to explore some of these ideas?
Well, there's been one of the ways of stabilizing a wormhole involves the Casimir effect, and there's some active physics investigations of the Casimir effect and its implications. However, you get a little bit of negative mass in the crack, but basically, if you take two conducting plates and move them close together, it suppresses some of the quantum fluctuations in the vacuum that between them, and the result is that you get a region of slightly negative energy in the gap between the plates, and this causes the plates to be pulled together a little bit, and you can measure that. And there have been some active investigations of that sort of thing, but the possibility of using that to produce enough negative mass energy to make a wormhole is pretty slim, I would say. The other thing that's perhaps possible, I mentioned Woodward's Mach's principle work. There are two terms in the equations. This is an interesting application of general relativity, because usually when one predicts what you get from general relativity, the numerator of the equation has a big G in it, and big G is a very small number, so it sort of kills all the things. It makes it very difficult to measure anything. The things that Woodward has been doing, big G is in the denominator, so you're dividing by a small number instead of multiplying by a small number, so it produces big effects. And there is a term in his work that if it's valid, and like I say, this is not ready for prime time yet, but it's being worked on. If it's valid, it offers the possibility of producing negative mass from this sort of Mach's principle stuff. And if you want to grasp at straws, that's perhaps one direction in which one can grasp for producing a negative mass that might be possible to make a wormhole from.
Last question goes to Paul Davies.
Well, it's a comment, really. I just wanted to clarify the business about stability of the wormholes from quantum field theory effects, because I've worked on that, written some papers. And what actually happens if chronology protection is correct is that the back reaction of the quantum vacuum with the negative energy that you're trying to assemble, the back reaction from the effect, one way of thinking about it is virtual particles going in closed loops through the wormhole and around again, is to prevent you creating the wormhole in the first place. So it's not so much you make a wormhole and there's a big explosion, it's that the back reaction of the quantum vacuum disrupts the very geometry you're trying to induce.
This is when it's going
energy.
time-like or or for any wormhole?
When you're trying to make the wormhole in the first place. So the chronology horizon that Stephen Hawking defined is, in effect, the energy piles up on that chronology horizon. It prevents you from making the wormhole.
Okay.
So that's how chronology protection would work. But of course, we'll only be sure of that if we have a fully functional theory of quantum gravity.
Right.
Let's thank John Cramer.